You're standing on the shore. The water is warm, the sun is blazing, everything is just how we like it. And then the sea starts pulling back, exposing the seabed, and so fast that within a couple of minutes it's already out of sight. Fish flopping on the sand, shells, all kinds of weird stuff that's usually hidden underwater. You'd probably think, lucky me, I can grab fish with my bare hands, and for free. But no, this is your cue to get your legs moving and get as far from the shore as possible. And right now, I'll explain why.
First, let me say that tsunamis have nothing to do with tides. The way the moon and sun drag the ocean back and forth twice a day. Regular waves, the ones surfers ride, are born from wind. Wind rubs against the surface of the water, stirs it into ripples, and the harder it blows, the higher the wave. But all that action only happens at the surface. The water underneath is completely calm. A tsunami works nothing like that. Wind has nothing to do with it. The action happens at the bottom, and what moves isn't the surface, but the entire body of water, from the seabed all the way to the top.
So what actually shakes the water from below? The most common cause is an earthquake on the ocean floor. Tectonic plates, those giant chunks of Earth's crust that entire continents sit on, slowly creep past each other, literally a couple of centimeters a year. But in the places where one plate slides under another, the edge sometimes catches and gets stuck. The plates keep pressing against each other. The tension builds up over decades, sometimes centuries, and at some point, the edge snaps loose. It's all like two wooden boards you're squeezing in your hands and slowly twisting. Nothing happens at first, and then crack, they snap with a bang, releasing all the built-up energy in a fraction of a second. Except instead of boards, a section of the seabed the size of a small country, and instead of a crack, a sudden vertical jolt of the ocean floor by several meters. That's what throws the entire column of water upward.
Sometimes the cause of a tsunami can be an underwater volcanic eruption, which literally blasts the water sideways with an explosion. Sometimes it's a landslide, when a chunk of an underwater slope breaks off and drops down, like someone knocked over a bowl of soup. And sometimes, though it's quite rare, something large falls into the ocean from outside, like a meteor, and creates a wave much like a stone thrown into a bathtub, only the scale here is a bit different.
The strangest thing is that in the open ocean, a tsunami is nowhere near a giant wall of water. The wave height there is usually less than half a meter. A ship that ends up right on top of this wave won't notice anything at all. It'll just rock slightly, like from an ordinary swell. And yet, the wave is racing at the speed of an airplane, 700, 800 kilometers an hour. And its length, the distance from one crest to the next, can reach 100 kilometers. This colossal mass of water moves all as one, from the surface to the very bottom. It's just stretched so far horizontally that the eye can't make out the difference. But when all that mass of water approaches the shore, everything changes. The seabed starts rising, the depth decreases, and the wave runs out of room. It can't just stop because it's carrying an enormous amount of energy, and energy doesn't vanish on its own. The wave slows down, sometimes drastically, but the height starts growing right before your eyes because all that energy that was spread out horizontally over 100 kilometers now has to squeeze into a much, much smaller space. This is called the Shoaling Effect, and this is exactly where a modest half-meter wave offshore turns into a wall as tall as an apartment building.
But why does the water pull back before the wave in the first place? A tsunami, like any wave, has a crest and a trough, and sometimes it's the trough that reaches the shore first. Then the sea level drops sharply. The seabed is exposed for tens, sometimes hundreds of meters,
And a person who's never heard about this has exactly one thought. Lucky me, I can walk along the bottom and see what's there. That's exactly what was happening in the Indian Ocean in 2004, when people were walking out onto the exposed seabed to photograph fish and collect shells, while a few minutes later, the wave itself arrived. Though this doesn't always happen. Sometimes the crest is the first to reach shore, with no warning in the form of retreating water, so you can't count on this sign as a guaranteed giveaway either. If you felt a strong earthquake on the coast, or you saw the sea pull back sharply and fast, don't run for the fish. Run inland and uphill to higher ground as fast as you can.
Can a tsunami actually be stopped? The short answer is no, but you can buy time. After the 2011 earthquake, Japan built a wall along its coastline about 400 kilometers long and up to 15 meters tall. Sounds reassuring. Except the problem is that before that, similar walls were only 5 to 10 meters high, and the 2011 wave simply went right over them. So dams and walls are a backup, not a guarantee, and relying purely on concrete isn't a great idea. What works far more reliably are networks of sensors and buoys out in the ocean, which give people at least a little time to get away on their own, away from the shore.
So let's go back to the beach we started from. The water has gone out, the seabed is exposed, and somewhere on the sand, a fish is flopping around, just begging to be grabbed. Don't. What you just learned in these past few minutes, not everyone standing on beaches like that one in December 2004 knew it. The difference between those who made it and those who didn't was, in some cases, exactly this one fact. The retreating water is not a gift, it's a countdown.